All right, I trust you did well on quiz 38. Students in here did fairly well. A few little things here and there, but for the most part, good job as we wrapped up circles. Your reading last night was all about parabolas. So next thing in your notes, let's go ahead and define the parabola. Now, we alluded to this once before when we worked on a locus problem, and we ended up discovering we got a parabola. So this isn't the first time you've heard of it. It's the first time I've had you write it in your notes. A parabola is defined as the locus of points equidistant from a given point and a given line. The locus of points equidistant from a given point and a given line. The locus of points equidistant from a given point and a given line. So if I have some line like this and I have some point, for instance, that's right here, well, obviously, right about here would be the same distance from both. But if I went over here, right about here would also be the same distance from both. Now, this distance is perpendicular, this distance is straight line, right? But if I went maybe here, this distance would be about the same as that distance. All right, you can see how we end up getting this parabolic curve, right? And so this parabola is the locus of all points equidistant from a point and a line. You need to write this term down. The point is called the focus. The given point is called the focus. And the given line is called the directrix. Directrix. Those are R's. They're just poorly drawn because I've never been good at lowercase cursive R's. All right, the given point is called the focus, and the given line is called the directrix. Now, if I were to, let's just draw some parabolic shape, because we're familiar from years past of what a parabola might look like. This focal point is going to be always contained within the parabola. The directrix will always be without the parabola. But you might recall from your Algebra 2 days that the point where the parabola suddenly changes direction is called the vertex. We'll label it V, but if you'll note that term in your notes, the vertex is the point at the parabola where it changes direction. The point where the parabola changes direction. And if you were to draw a line, we'll label the focus here as F. We've already got that term in the notes. If we're to label this point as F, if I were to draw a line through V and F, we'd have a line called the axis of symmetry. The axis of symmetry is simply the line through V and F, the line through the vertex and the focus. Not the line segment, but the actual line. Normally, this axis of symmetry will either be the x-axis or the y-axis. It can be adjusted with an xy term, but we're not going to. So for our purposes, this axis of symmetry will either be x or y. I've drawn it as a slant because, I don't want you to get consumed that it's always this way or always that way. But generally, it'll either be an up parabola, down parabola, left parabola, or right parabola. Okay? Now, obviously, if we were to measure the distance to the focus, that same distance from focus to vertex would have to be the distance from vertex to directrix. And so the directrix is always going to be this same length outside, and it'll always be perpendicular to the axis of symmetry. We'll label this directrix DD prime. But again, it's simply going to be whatever this distance is away here. And of course, all of these points will have the same distance to the directrix as they would back to the focus. This is poorly drawn, but for illustrative purposes, our directrix will always be perpendicular to the axis of symmetry. That bears writing down. Directrix will be perpendicular to the axis of symmetry. Now, to help us get a good parabolic curve, we need a couple more points to help us in our graphing. Of course, you will be using a lot of graph paper in this chapter. So what we're going to do is we're going to understand this, that through the focus, I could draw a lot of different chords. Right? A chord is any line that starts and ends on a circle. That's how we define it in geometry. Well, really, it's any line that starts and ends on a conic. Right? A circle being one of our conics. So these are all focal chords because they go through the focus, right? Not vocal chords, but focal chords. There's one special focal chord, though, And that's the one that's perpendicular to the axis of symmetry, thereby being parallel to the directrix. Two lines perpendicular to the same line, parallel to each other. This is called the lattice rectum. The lattice rectum. Lattice, Greek for line, rectum, Latin for right, or right angle in this case is implied. We'll label it LR. So we don't really care about all these other focal chords, but we do care about the lattice rectum, specifically getting the endpoints of the lattice rectum, as those endpoints will allow us to get a good parabolic curve, understanding the shape that we're looking for. So several parts to our parabola that we need to know. Now, we've talked about this term once before, several times before really, is the eccentricity. Now, to this point, I've just let eccentricity be defined as the uniqueness of the conic. But eccentricity is actually defined, if you write this down, as a ratio of distances. Now, in the case of a circle, it's not, because there aren't multiple distances you can use in a circle. It's always just the radius, if you will, and the eccentricity is 0. 0 doesn't give you a ratio necessarily, so we don't think of it in that terms for a circle, but for all of our other conics, eccentricity is going to be a ratio of distances. For the parabola, the eccentricity of a parabola is always defined as the distance of any point in the parabola, whether it's this point, this point, this point, that point, this point, this point, whatever, right? The distance of any point to the focus compared to the distance of that point to the directrix dd prime. And because, and again, this is poorly drawn, but if it's a true parabola, this distance to focus and the distance to the directrix have to be equal, because that's the definition of a parabola. The locus of points that are equidistant from the focus and the directrix. So since these are always equal, if you divide something by its equal, you always simply get 1. So for every parabola, the eccentricity will be 1, which is why we're studying it second. The circles always have an eccentricity of 0. Parabolas always have an eccentricity of 1. So we're going to take the two easy ones. Then the weird ones come later. But for now, we'll deal with these two. When you're working with a parabola, your form will always be x squared or y squared plus ax plus by plus c equals 0. Where with the circle, it was x squared plus y squared plus ax plus by plus c equals 0. With the parabola, it's either going to be x squared or y squared. This is the only conic with one squared variable. It's the only conic with one squared variable, which makes it really easy to spot. If only one of them squared, it's got to be a parabola. Now, we've seen this before, though, haven't we? For instance, if I had the equation back in chapter 10, y squared equals x plus 4. Well, remember, we would identify the x-intercept and the y-intercept, and we'd identify whether it was symmetric to the x-axis, y-axis, origin. We would analyze the domain and the range. Remember all of this? But one of the things we identified quickly is that only one is squared. We know it's going to be a parabola. What would be the x-intercept here? Negative 4. 0. What about the y-intercepts? Positive and negative 2. Right? Would it be symmetric to the x-axis? Yes, because you can plug a negative in for the y. Would it be symmetric to the y-axis? You can't plug a negative in there. What about to the origin? Guaranteed no, remember, if one of the first two don't match. What about the domain? All possible x values. Remember, for that, we'd have to solve for the other letter. What are the limitations on what I can plug in for x? Right, negative 4 or bigger are fine, right? And then what about the range? Well, here we'd solve for the x, so y squared minus 4 equals x. Limits on what I can plug in for y? All real numbers. Right, so we could graph a parabola largely using this analysis here, right? We have our x-intercept at negative 4, positive negative 2, and so we know we get kind of a skinny-looking sideways parabola here that's symmetric about the x-axis, nothing else. We see our domain pictured there. Remember doing this? Okay. For that matter, if I had something like x squared equals 6y, we could do the same kind of analysis. If I said x squared equals 6y, well, what's the x-intercept?
0.
What about the y-intercept?
0, 0.
Yeah, so here the graphing became a little harder because I only had the 1 point, right? X-axis symmetry?
No.
No. Y-axis?
Yes.
Yes. Origin?
No.
Guaranteed no, which means it's either going to go up symmetric to the y, or it's going to go down symmetric to the y. Domain?
All real numbers.
Yeah, if we get the y by itself, I mean, I can plug in anything. What about the range? If you get the x by itself?
All no. 0 to infinity.
0 to infinity, right? Positive numbers. And that tells me it's going to go up. So this kind of analysis was good for telling me it's going to be an up parabola. But is it going to be like that? Or is it going to be like that? Or is it going to be like that? Or is it going to be like that? You get the idea. There's a lot of different parabolas we could draw. So those analytic tools in the first case worked pretty well. I pretty much knew the shape of the parabola because I had intercepts everywhere. Here going to be a little bit more of a challenge, right? But I could still kind of get the basic idea. So there's a better way, and it's what we call the parabola form or the parabolic form of a conic. Don't get this in your notes. The parabolic form, there's actually going to be 2 of them depending on which variable is squared. Okay, so for the parabolic form, it's either going to be y squared equals 4px, or it's going to be x squared equals 4py. Y squared equals 4px, or x squared equals 4py. Now you're like, okay, I recognize the x squared and the y squared, one squared variable, one not. What's up with the p and the 4, right? Well, a couple different things for you to get in your notes. First of all, the p is the focal length. The p is this focal length. And this chalk is not showing up well like that, so we'll do it like this. This length from vertex to focal point, that's the p value. Okay? By the way, this right here would also be p, wouldn't it? It would just go the other direction. It could be thought of as negative p, if you will. But that would be from vertex to directrix. So p is the focal length. That's vertex to focus. Second thing that you need to know, the non-squared variable is the axis of symmetry. Think about it. If I ask, is it symmetric to the x? Yes, because I can plug a negative in for the y. Is it symmetric to the y? Yes, because I can plug a negative in for the x. Always the axis of symmetry is the non-squared variable. Since there's only one of them that's squared, then one that isn't squared is your axis of symmetry. The next thing we need to know about this parabolic form is that the vertex is assumed to be at the origin. For now. For now, we'll assume in this parabolic form that the vertex is at the origin, which is what we saw a moment ago, didn't we? We had the x squared equals 6y. Well, do you see how that's basically in this form? X squared equals something y, right? And so we could see it was y-axis symmetry, right? It was up or down. And we saw that the origin was our vertex point, where it pivoted, if you will. The last thing, though, the thing that we hadn't solved yet was this focal length, right? This 4p is the 6. Well, if I were graphing this, let's think about it. If 4p equals 6, then what is p?
3 halves.
3 halves, or 1.5, right? Well, that means from vertex to focal point is 1.5 units. That's where the focus would be. By the way, if you went down 1.5 units, you get to the directrix, right? So here'd be my focus, here's my vertex, there's my directrix. But to tell you how wide or narrow the parabola is, we use this right angle perpendicular focal chord, the lattice rectum. You need to know that the length of the lattice rectum is equal to the absolute value of 4p. The length of the lattice rectum, because the length isn't positive or negative, right? The length of the lattice rectum is the absolute value of 4p. Well, the 4p is the entire coefficient of the non-squared variable. That means that the lattice rectum is 6 units long. Well, notice the positioning of the lattice rectum. Because of the parabolic symmetric shape, If the whole thing is 6, how big is this side?
3.
And this side? The other 3, right? So therefore, each side of the lattice rectum is the absolute value of 2p. So half of this on one side, 1, 2, 3. Half on the other side, 1, 2, 3. And if we were to draw the lattice rectum, that's how wide it's going to be. That tells me exactly how wide to make my parabola. And that's really what we needed to know. It's how wide do I make it? The lattice rectum tells me how wide to make it. Now, some errors that we might make here. One of the errors might be we go through the lattice rectum and like straight line up. Well, we're not trying to draw the letter U here, right? We're trying to keep a nice smooth curve. This didn't go smoothly, did it? So as we curve through, just kind of keep a nice basic shape going. I like to kind of redraw to kind of keep the same shape on both sides. Okay? But some nice smooth shape with the lattice, the vertex positioned here. Focal length tells me how far to go to the focus. And then really, if you think about it, you would almost double the focal length. Or cut this number in half to tell you how far each direction to go. And that gets us a curve at this point, this distance to focus, that same distance to directrix. And that would be true of every point on the curve. All right, so let's go and actually graph some of these. Get some graph paper out now. And let's use this parabola form or parabolic form to graph some parabolas. We're going to do a few parabolas on each Cartesian plane because we're lazy. We go ahead and set up a Cartesian plane. Let me see if I can zoom in just a little bit closer here. If you have different colors of ink or colored pencils or something like that, it might behoove you to use those as we go through different parabolas. Go and write this down if you would. X squared equals negative 4y. There are basically 4 things we want to analyze about our parabola. Once we've identified, of course, that it is a parabola, because 1 squared and 1 isn't. First thing I always want to know is where's the vertex? Where is the starting of all of this? But we said for now, class, the vertex is just going to be at 0, 0. So there's really not a whole lot of suspense in that yet. We'll get to the point where, like a circle, we can translate its origin. We can translate this vertex later, but for now it's just going to be 0, 0. The next thing that I always want to know is what is the axis of symmetry? Is this a sideways or is it an up-down? Well, in this case, which axis is the axis of symmetry? The y, the non-squared variable. So that means this is going to be an up-down parabola. Make sense? The next thing I want to know is what is the focal length? Remember, the focal length is represented by the seemingly random letter P. I mean, listen, focal length. P makes a lot of sense, right? Well, remember, the form here is x squared equals 4py. The coefficient of the non-squared variable is the 4p. So what is p? What is the focal length? Negative 1. And then the last thing we need to know is how long is the lattice rectum? Though I generally look at it as one side. How long is each side of the lattice rectum? Well, remember, the lattice rectum's whole length is the 4p's absolute value. We don't worry about positive, negative, but this is the whole thing. Each side then is the absolute value of 2p, or basically ignore the sign and double it. So 2. So what I want you to do on your graph paper is start by plotting the vertex at 0, 0. From here, on the y-axis, we're going to go negative 1. That's my focus. I've got my vertex, I've got my focus. By the way, if you go down 1 to the focus, we need to go the opposite direction, up one, to that line called the directrix. Say that with me, class? Directrix. Again? Directrix. There we go. Remember, the definition of a parabola is the locus of points equidistant from a given point, focus, and given line, directrix. Finally, we're going to go ahead and plot the lattice rectum lengths, 2 on either side. Now remember, this has to run parallel to the directrix, perpendicular to the axis of symmetry. So we're going to go 2 units here and 2 units there. 2 in each direction for a total length of 4. If you want to draw the line itself, you can. You don't have to actually draw the lattice rectum. I like to label the ends L and R. So directrix is DD prime, lattice rectum is LR, vertex V, focal point F. And then starting at the vertex, don't straight line, curve your way through. And then kind of retrace the curvature you did on one side and use it to kind of set your mind for the curvature on the other side. And there we've got a mostly decent parabola. Again, graphed quickly by simply analyzing the equation, hence analytic geometry. Let's do another one on the same graph, but maybe switch to a different color of ink, or if you use pencil, use pen. If you used pen, maybe use pencil. Let's take a look at this one now. Y squared equals 10x. Y squared equals 10x. When we go to graph the parabola, the first thing, of course, we want is the parabolic form, which here is going to be y squared equals 4px. First things first, we need to know where is the vertex. And for now, I said the vertex is going to be at 0, 0. Next thing we always want to know is which axis is the axis of symmetry. And in this case, which is it, Jamie?
The x-axis.
The x-axis, the non-squared variable. Next, I need to know the focal length, represented by, well, the focal length is the p. The 4p is this number, but p would be a fourth of that. 2.5. 5 halves are 2.5 is my focal length. Finally, I need to know how long is each side of the lattice rectum. Again, 2 ways to look at this. That is the lattice rectum, which means it's a wide parabola, isn't it? And that's a big number, 10. It's a very wide parabola here. All right, but we're going to cut it in half, so, or you can think double the focal length, and that would give it to you as well. So using the same graph that we did a minute ago, let's put our vertex at 0, 0. So I'm just putting it right on top of the yellow dot. Still my vertex. And then along the x-axis go
To the right.
2.5, positive 2.5, right? If they wanted me to go backwards, I would go negative 2.5. But it said positive 2.5. There's my focal point. By the way, I will go negative 2.5, but not to the focus, but to the directrix. What is it, class? Directrix. It helps to direct the parabola, if that helps you think of it. So we're going to go 2.5 to the directrix. And then each side of the lattice rectum is going to be 5. And again, it's going to run parallel to the directrix, so perpendicular to this axis of symmetry. I'm going to go up 5, and I'm going to go down 5. Again, I'm not going to actually draw this lattice rectum, but I will label the endpoints L and R. The key is to slowly curve my way through from V to R, and then I'm going to go back through the V and go through the L. I mean, a very wide parabola this time. And we knew it would be wide because it has a very large 4p or lattice rectum value. Questions on this? All right, I want you to try one now at your seats. Might be able to use the same graph grid again, might not. Y squared equals negative 12x. Your turn to analyze and graph. I'm going to go ahead and set up a new graph grid for myself while you're graphing. But you may use the same Cartesian plane if you want. Where's the vertex?
0, 0.
Of course. Which axis is the axis of symmetry? X-axis. So it's a sideways parabola. Focal length? -3. And so each side of the lattice rectum? 6. Because the whole length is 12, so half each side is 6. So, did you plot your vertex at 0, 0? And then go backward 3 on the x-axis to your focal point.
I didn't have the negatives for 3.
Okay, does that make sense?
Mm-hmm.
All right. So then if we go backward 3 to the focus class, you need to go forward 3 to the directrix. There we go. Again, this isn't an asymptote, but we draw it dashed like an asymptote. Each side of the lattice rectum is 6. So since the axis of symmetry is x, from the focus I need to go up 6 and down 6. Very wide parabola here. And I'm going to start by curving my way very slowly. And then I'm going to kind of retrace. And there we go. Very wide parabola there. Did we have something similar? Right? Went sideways the other way. Is that correct?
The other way, yeah.
Okay. All right. Had it? Questions on this? All right, for homework, I want you to do 2 parabolas. You can do them on the same Cartesian plane. Y squared equals -8x, and x squared equals 2y. Okay, so just 2 for homework this evening. Do them on a new Cartesian plane, but do them both together because you're lazy like that. Maybe do them in separate colors would be nice if you have that capability. Maybe 1 pen, 1 pencil. We'll take a look at these tomorrow. And we'll take a look at your quiz that you took earlier in the hour, and we will go from there. And have a wonderful rest of your day. When the bell rings, you'll be dismissed.